Hi everyone. Dear friends, in this lecture video, I am very pleased to give the description about the various vapor power cycles. In my earlier video, I could share a synoptic overview about vapor power cycles. I could tell the contents in depth. But today, in this lecture video, I'll be very happy to convey the description, theoretical description concerning with the 5 standard vapor power cycles. In my earlier videos, I could deliver the content concerning with air standard cycles, internal combustion engines, gas turbines, jet propulsion. Even in the previous video, I could cover the synoptic overview, what exactly a faculty has to convey or what students should learn. That was covered. But today, in this video, I will be very happy to display the temperature entropy plot for 5 standard vapor power cycles. You know that for the further air standard cycles, it has 5 children. Carnot, Otto, Diesel, Dual and finally Stirling cycle. Usually what analogy I can give, in Mahabharata there were Pancha Pandavas, 5 Pandavas. Here also air standard cycles has 5 children. Analogously, when we take up the idea steam or vapor power cycles, even this family or this parent has 5 children. Who are those? To begin with, the eldest son or daughter Carnot cycle, followed by Rankine, reheat, regenerative, and lastly binary vapor power cycle. I wish to give the description for each and every cycle so that solving illustrative problems shall be easy for every individual. In my previous video, which was covered on the synoptic overview about vapor power cycles, I could just tell brief information about vapor power cycles. But in this video, along with the TS plot, let me take up the description. I have given the technological relevance, the application part and the benefits of learning vapor power cycles. In a line, let me tell, you may ask the application of vapor power cycle. Friends, in power stations, we will come across the relevance of these cycles. Now, without wasting much time, let me take up the description. As said, the parent steam or vapor power cycle has 5 children. I will begin with Carnot cycle. While studying air standard cycle, the first one was the reference cycle, Carnot cycle. It was conceived by one of the very famous thermodynamicist cum physicist, Nicolas Leonard Sadi Carnot. He was a French scientist cum physicist who could conceive the engine which is named after him. Many of the principles was propounded or formulated by Sadi Carnot. Even though his lifespan was just 24 and odd years, he could do many things. In air standard cycles, while studying the theory of heat engines, we could come across Carnot air power cycle. But now it is steam or vapor power cycle, very much applicable for steam power plants. When we see to the TS plot, whatever TS plot we could write in air standard cycles, the same. In a Carnot cycle, we find four thermodynamic processes. They are two isothermals followed by two isentropics. When we observe process 1, 2, it is unquestionably isothermal NTS plot. Next 2, 3, it is isentropic or reversible adiabatic expansion process. Next 3, 4, it is yet another horizontal line isothermal compression. Lastly, it is 4, 1, reversible adiabatic or isentropic compression. One heat addition, the other one heat rejection. So the same concept can be understood here, but we are learning steam power cycles. When this is pertinent to steam power plant, no doubt we have to depend on pressure process. Okay? Here, when we take up the PV plot, we consider constant pressure. Temperature stabilizes, but we depend on constant pressure process throughout. Let me take up the analogy. While taking the theory of heat engines, we totally depend on the function of a engine. But here, when we take up the relevance to steam or vapor power cycles, unquestionably, what are all the principal components? One is the feed pump, boiler, steam turbine, condenser. When we could learn the synoptic overview of vapor power cycles in the previous video, it was very much clearly taught, clearly explained. This is very much analogous to the module gas turbines. When we sketch the temperature entropy plot, we find four components: compressor, combustion chamber, next gas turbine cooler. Here, the names are different, but the principle of operation remain the same. In place of compressor, we are using yet another power absorbing device called pump. Next, in place of combustion chamber, it is boiler. Boiler do have combustion chamber. In place of gas turbine, we find steam turbine. Next, in place of cooler, we have condenser. The names are different, but the principle of operation remain the same. That's why when we get to know the idea about air standard cycles, gas turbines shall be easy. When we learn air standard cycles followed by gas turbines, learning vapor power cycles will be cakewalk for us. Okay? That is all regarding Carnot cycle. You all know practically it is not viable. There are some limitations. In case of Carnot vapor power cycle, it is not possible to compress the wet vapor isentropically. Next, it is not possible to judge or adjudicate the quality of condensate. So, like this, we have two or the other limitations wherein practically it is not viable. That is why this is just taken as a reference. Next, when we need to calculate thermal efficiency, usually what is the expression? You all know it is work done divided by heat added. Work done we normally take as heat added minus heat rejected. Here also we can use the same. But on knowing Carnot cycle, the next cycle very practical based, that is Rankine cycle. In the previous video it was clearly said we find 3 R's: Rankine, reheat, regenerate. Purely practical based cycles. Let me take up the description. Kindly observe the temperature entropy plot. We have taken 2. One is the Rankine cycle by simple form. Next is the actual cycle. As just said, we find 4 principal components in a steam power plant: feed pump, boiler, turbine, condenser. When we observe the temperature entropy plot for a simple Rankine cycle, we find the processes. When we observe here, this is the feed pump. Very close to the boiler, feed water plant is juxtaposed. You find water treatment plant. In a human body, continuous circulation of water is important. Likewise, in a boiler, feed water is important. Who is the person responsible for feeding feed water to boiler? It is feed pump. It goes to boiler. Beneath the boiler, we find combustion chamber. Combustion phenomenon takes place. So high pressure, high temperature gases goes to a steam turbine. Their expansion takes place. We expect high velocity jet. Next it comes to condenser. Cooling process takes place. Heat rejection takes place. This is all regarding Rankine cycle. Rankine cycle is basically a theoretical cycle wherein steam turbine works. This idea was conceived in 1820 by a Scottish engineer and polymath who was with University of Glasgow. He is none other than Sir William Mohan Krishna. He, along with two other thermodynamicists, one a German physicist by name Rudolf Julius Emanuel Clausius, and the other was a British physicist, Lord Kelvin alias William Thomson. Sir William Thomson is the real name for Lord Kelvin. Since he was in a village Kelvin, he is very popularly called Lord Kelvin. He is regarded as the father of thermodynamics. Okay? Right. So this is the simple Rankine cycle where we find four components: feed pump, boiler, steam turbine, condenser. But below that, we have some sort of modification. There is no much change. Sometimes in any numerical problem solving on Rankine cycle, boiler pressure and condenser pressure shall be given. We will be asked to solve for cycle thermal efficiency. In the second variety of problem on Rankine cycle, modified Rankine cycle, we find boiler pressure along with superheated temperature. For this variety, we may have to refer thermodynamics data handbook, which is table 1, pressure basis. But below, along with the boiler pressure, superheated temperature has been given. For that, small modification has been encumbered. This clearly, the shape of the aileron in an aeroplane, very similar to that depicts principle of superheat. So when we solve numerical problem on Rankine cycle, please be clearly aware, simple Rankine cycle, just boiler and condenser pressure shall be given. This is the boiler pressure, this is the condenser pressure. But here, along with the boiler pressure, you find superheated temperature. For that, we have to refer the properties of superheated steam. Normally, it is table 3. Okay? Kindly be aware of the principle of operation clearly. Feed pump, boiler, next steam turbine. In a steam turbine, we can expect the generation of mechanical energy. But when an electric generator or an alternator is coupled, we can expect electrical power generation to happen. Next, before this, we find condenser pump. Condenser, condensate pump. Okay? So, condenser, it will happen. Condensation will take place. But before that, we find cooling coils being incorporated in the condenser. Once after the condensation takes place, condensate shall be obtained. For that, to check the quality, we have condensate pump. Next, feed pump. Clearly be aware of the principle of operation. Next, reheat cycle. We are aware of Carnot cycle. Next is the Rankine cycle. Now it is reheat. The term reheat is not a big issue for us. Why? Because in one of my lecture videos, I have covered gas turbines comprehensively. When we were learning the methods to improve the cycle thermal efficiency of gas turbine, one method was clearly taught. What was that? Reheater based gas turbine. You all know that a reheater shall be incorporated between high and low pressure turbine. That is what it has been shown. When we compare this with the Rankine cycle, in Rankine cycle we have one turbine, one steam turbine. But here you can see to the shapes, two shapes you can observe. Feed pump, boiler, no change. Here we have single turbine, but here we have two turbines. High pressure turbine, low pressure turbine. Between that, process of reheating take place. When process of reheating take place, naturally high pressure gases shall be metamorphosed into low pressure gases. Ultimately, we expect high velocity jet of steam to take place. This can even be referred to as Rankine reheat cycle or reheat Rankine cycle. Just depending on the principle of operation, reheat cycle work. Sir, what are all the principal components in this? The same. Feed pump, boiler, turbine, condenser, condensate pump. But we have two turbines. That's why when you know gas turbines clearly, learning this shall not be a difficult task. So why process of reheating take place? Why? Because higher magnitude of pressure shall be converted into lower magnitude of pressure. Okay? This is all about reheat cycle. But how about the problems? When we take up the problems, we usually calculate the cycle thermal efficiency of Rankine or reheat cycle. Next, we calculate net work done. Next, we will take up work ratio, eventually calculation of specific fuel consumption. How to calculate cycle thermal efficiency when a problem is taken on Rankine or reheat cycle? The same. Cycle thermal efficiency is what? Work done upon heat added. When we were solving a problem on gas turbine, it was turbine work minus compressor work. But here, in place of compressor, which is the other power absorbing turbo machine we are using, it is feed pump. Pump is unquestionably power absorbing machine. So here, net work, how do you calculate? Turbine work minus pump work. When we know that, we can calculate work ratio. Work ratio is what? Net work to turbine work. So calculation is simple, but as I clearly revealed in the previous lecture video, we are supposed to use thermodynamics data handbook or steam tables clearly. Without employing that, we will not be in a position to tabulate the values of enthalpy, entropy and specific volume. Please be clearly aware that we will be using thermodynamics data handbook. Next, penultimately we need to use regenerative cycle. Even the term regenerative is not new to us. When we could learn Stirling cycle, did we not use a regenerator there? In air standard cycles, when we drew the TS plot, it comprised two isothermals, two constant volume processes. That is the only cycle wherein we don't find isentropics. Fine. In that, did we not use a regenerator or heat exchanger? Yes. One of the methods to improve the cycle thermal efficiency of gas turbine, regenerative based gas turbine, we could study recently. Here also the same. Along with the components, feed pump, boiler, steam turbine, condenser, condensate pump, we will be using reheater here. But in the case of this, we will be using an heat exchanger. Regenerator, it is a very professionally structured term or coined term. Heat exchanger in the colloquial context. In a regular parlance, we use two or more heaters to achieve the process comprehensively. That is why it is regenerative cycle. Since we are using two or more heat exchangers, depending on the requirement, we take up the temperature entropy plot in this way. If we use two heaters, this way. If we use three heaters, one more block we have to keep it. Once when we are aware of Rankine cycle, learning reheat and regenerative shall not at all be an ordeal for us. But to know reheat and regenerative cycles, kindly be aware that you should be comprehensively be well acclimatized with the learning of gas turbines. When we know the methods to improve cycle thermal efficiency of gas turbine, these things will be easy. We could clearly collect information regarding 4 children. Okay, one the eldest Carnot cycle, reference cycle, 3 practically based cycles: Rankine, reheat, regenerative. Okay, 3 R's. Don't forget that. You should be properly be aware of the TS plots. Lastly, what is that? Here the 5th son for steam power cycle or 5th daughter. He or she is the binary vapor power cycle, which is very unique when compared to all. In the conventional era or epoch, we were not aware of this. But now, to improve the overall efficiency of the plant, we will use binary vapor power cycle. What is that binary vapor power cycle? Binary meaning dual, 2. In a single unit, we will be very much pleased and privileged to use 2 cycles or 2 working fluids. Normally, the first one will be the steam. The second one shall be mercury cycle. We will be using 2 fluids. One is the steam, the other one can be mercury, diphenyl oxide, ammonium bromide, like that. Okay, depending on the requirement or prerequisites, we have to satisfy that. So what is the purpose of using binary vapor power cycle? That has the potential to aggrandize or augment the overall efficiency of the plant. So this is what the theoretical detail one has to be clearly aware of. Okay? Now I will consolidate the information so that you will get the summary of it. Friends, steam or vapor power cycles, when we need to know, we should be aware of the relevance, application aspect. What is that? It is very much clear. We will be using in steam power plants. Earlier for year standard cycles also it comprised 5. Carnot, Otto, Diesel, Dual and Stirling. So 2, 3, 4 were very important. Here also 2, 3, 4 are highly practical based. We could learn the theoretical description for Carnot, Rankine, reheat, regenerative and eventually binary cycle. When we get the theoretical picture regarding Rankine cycle, we need not have to worry. Okay? Say while learning Rankine cycle, there may be a question. How we can increase the cycle thermal efficiency? For that, we may have to increase the boiler pressure. Next, we may have to reduce the condenser pressure, adopt regenerative feed water heating. Next, we can employ regenerator system. Next, we can take up binary vapor power cycle. So, these are all the various methods to improve cycle thermal efficiency. So, friends, listen to this lecture video very seriously. Solving a numerical problems on this shall be easy. Also, please be aware of the use of thermodynamics data handbook, particularly for the modules like steam power cycles, refrigeration, air conditioning. You are supposed to use that clearly. Without knowing how to tabulate the values of enthalpy, entropy, specific volume, you will not be in a position to solve even an entry level problem. Okay? If you like this video, you can share to n number of people. Let all be benefited in learning the applications of thermodynamics. Thank you very much. All the very best.